Okay, so jumping right into it today, we are going deep into the world of reward modeling. Now, for those of you listening who already have a good grasp of machine learning, you know that having solid feedback systems are absolutely key when it comes to guiding these large language models, the LLMs. And RL, reinforcement learning, especially after the LLMs have already been trained, that's become a pretty standard way to make sure they're behaving like we want, helping them reason better and getting them to adapt to all sorts of different situations they might come across.
You're spot on. The reward model is really the heart and soul of making RL work well for LLMs. It's the part of the system that creates those crucial signals that steer the learning process. And, what we're really interested in today is a big challenge in this area. How to build reward models that can handle the huge variety of real-world queries that are out there. We want to go beyond just those very specific, tightly defined tasks.
Right, exactly. We've definitely seen a lot of progress in reward modeling for those specific domains where the evaluation is very clear cut, like when it comes to solving math problems or generating code. But things get way more complicated when we're talking about general language understanding and how these models actually produce language. Because, how do you reliably score the quality of a response when there isn't always a clear cut right or wrong answer?
That is the million-dollar question. And it's exactly what we're diving into today. We are exploring the newest developments in generalist reward modeling, and especially the trickiness of getting reward signals that are both accurate and meaningful for a wide range of inputs that could come up in the real world. And then there's another layer to this. How well these models can actually take advantage of more computing power when they are being evaluated to improve how they perform. We call this inference-time scalability.
And so, to kind of map out our discussion today, we are going to be focusing on a paper titled Inference-Time Scaling for Generalist Reward Modeling. This research really delves into how giving more compute power to the reward model while it's being evaluated can make it more accurate. And importantly, it looks at how the way these models learn impacts how well they can scale.
Right. And a central idea in this paper is the introduction of something called self-principled critique tuning, or SPCT for short. The authors propose this new learning framework as a way to make those reward generation processes much better at utilizing all that extra computing power during inference. Our goal today is to really break down this research and see what it means for how we align LLMs in the future.
So let's just start by laying out the main hurdles that researchers face when they're trying to develop these generalist reward models. You touched on the contrast between this and those more rule-based tasks. Could you maybe unpack that a little? Like, why is generating these high-quality rewards for more general queries so much more difficult?
Well, the biggest challenge is that for a lot of how language is used in real-world situations, there are no explicit, universally agreed upon references or like a single objective truth. Think about it. If a user is asking for some creative writing or they're looking for advice on a really complex personal issue, there are so many factors that go into evaluating the quality of the model's response. Was it actually helpful? Was it safe? Was it clear? Unlike solving a math problem or writing a piece of code, the criteria here are way more subjective. It's not a simple right or wrong. And this makes designing a reward function that can actually capture all of these different, often unspoken dimensions extremely difficult.
It sounds like the evaluation goes far beyond just, checking the facts. You're looking at all these subtle qualities that are just harder to measure with the usual metrics.
Precisely. And that's why we need reward models that are not only general, meaning they can handle all kinds of different input formats and stay accurate across different domains, but that also scale well during inference. What we want are models that get better and better at generating those reward signals, the more computational resources we give them during evaluation. And it's not just about the resources. The learning methods used to train these models have to actively encourage this kind of scalable behavior so they can really benefit from that increased compute. A key point to understand is that with SPCT, these reward models can become more accurate and reliable simply by giving them more processing power at the evaluation stage, without the need for constant retraining or using absolutely massive models.
Now, the paper talks about different ways to generate rewards, like scalar, semi-scalar, and generative methods. And then it mentions pointwise and pairwise scoring. They've got a nice visual breakdown in Figure 2. Can you walk us through those and talk about what limits them in terms of flexibility and scalability?
Sure thing. Each of those has its own strengths and weaknesses. Pairwise reward models, which basically learn by comparing two different responses and figure out which one is better, they're really common. But because of how they're built, they're not that great at evaluating a single response on its own or when you need to compare more than two at the same time. To do that, you'd have to do a bunch of separate pairwise comparisons, which is not very efficient. So they're a bit limited in terms of input flexibility. Now, scale reward models, on the other hand, they just spit out a single numerical score. They're super efficient in terms of computation, but they often can't really capture all the nuances of a response. Like the paper points out, scalar models have trouble generating different reward signals for the same input across multiple inference runs. And this is crucial for taking advantage of those sampling-based scaling techniques, where you evaluate a response multiple times and then combine the results.
So it sounds like a scalar model might keep giving you the same score no matter how much compute you throw at it during inference, which essentially puts a hard limit on how much better it can get.
Exactly. And then you have generative reward models. They produce an actual text critique as the reward, which gives you way more flexibility and the ability to give more detailed feedback. Point-wise GRMs, they're defined in equation 1 of the paper, and they're really interesting because they can handle single responses, pairs of responses, and multiple responses all within the same language-based structure. So in equation 1, they define point-wise GRM, where you have a query X and several responses. The reward function then creates a critique, C, and from that you get an individual score. The paper says these scores usually fall within a range of 1 to 10. What this means for you is potentially huge. It suggests that maybe you don't need the biggest, most powerful models to get cutting-edge results. In reward modeling, you can get there by using your existing computational resources in a smarter way during inference.
The authors specifically chose to use that point-wise generative reward modeling approach. Why did they go with that one?
Well, the big plus with point-wise GRM is how well it adapts to different numbers of responses. It's all handled within the same language framework. And as we've talked about, that unified approach is super important for building a reward model that's truly general. It's all laid out in equation 1. The model produces a critique in regular language, and then a specific score is pulled from that. This allows for capturing more complex reasoning and providing more nuanced feedback than just a simple numerical score.
Now, the paper then goes on to explore how using principles, which they borrow from the concept of constitutional AI, can guide this reward generation in more general situations. Can you explain that idea and why it matters here?
So with constitutional AI, you basically give these LLMs a set of guiding principles, a constitution, if you will. It's like giving the AI a set of high-level rules to follow when it generates responses or evaluates data. And the authors of this paper saw that in general domains, where you don't always have clear-cut rules, these same principles could be used to guide how the reward model evaluates things. Instead of relying on very specific handcrafted rules that only work for a certain task, the reward model is given broader principles to work with, like helpfulness, accuracy, safety, or clarity. It's then tasked with evaluating responses based on these principles.
So they did an initial experiment, which they detail in Table 1, to see how this approach would work. They compared principles that the LLM came up with itself to principles that were filtered based on their alignment with ground truth rewards. What did they find?
The really interesting thing was how different the performance was depending on the principles used. The principles that were generated by a more powerful model, they used GPT-4 in this case, and then filtered to make sure they aligned with the ground truth rewards, those actually led to a big improvement in reward quality, both on the chat-hard and IQ-evil datasets. But the principles the model generated by itself, those only resulted in small improvements. This really highlights how important it is to have good, relevant guiding principles. Just having any old set of principles isn't enough. They have to be truly aligned with what we consider a high-quality response.
And that brings us to the paper's biggest contribution, self-principled critiqued tuning, or SPCT. Can you tell us more about this new learning method and what it's trying to achieve?
SPCT is the heart of this paper. It's all about making point-wise generative reward models better at scaling during inference. The goal is to get those GRMs to generate better rewards when we give them more computing power during evaluation. It works in two main stages, and they've illustrated it nicely in Figure 3. You start with what they call rejective fine-tuning, RFT, to get things going. Then you move into a phase of rule-based online reinforcement learning to refine the reward generation by improving both those guiding principles and the critiques themselves. The figure shows how this two-stage approach really helps boost the model's ability to scale.
Let's take a closer look at that first stage, the rejective fine-tuning. What's the purpose of that initial cold start phase?
The main goal there is to teach the GRM how to generate those principles and critiques in the right format so it can handle a wide range of inputs. Because we're working with a point-wise GRM, it has to be able to evaluate single responses, pairs, and even multiple responses, all within the same consistent language structure. Some earlier work used different formats for different numbers of responses, but this approach is all about keeping things uniform. The data they use for training in this phase is a mix of general instruction data and trajectories sampled from pre-trained GRMs. They pull these trajectories from existing reward modeling datasets that already have different numbers of responses. These trajectories are sampled multiple times, NRFT times to be exact, and then they use a rejection mechanism based on how well the predicted rewards line up with the ground truth. So if the model predicts the rewards incorrectly, that trajectory is thrown out. They also discard query response pairs, where all the sample trajectories are correct because those are considered too easy.
You mentioned something called hinted sampling, which is an option during this RFT phase. What exactly is that?
Oh, that's an interesting twist. With hinted sampling, they sometimes give the model a little nudge by adding the ground truth best response to the prompt while it's sampling. The idea is that by providing this hint, the model will be more likely to generate critiques and rewards that actually match up with the correct answer. But they only reject trajectories if the model's prediction is still wrong, even after getting the hint. They notice that while this hinting can be helpful early on, it can sometimes cause the GRM to become too reliant on it, maybe skipping over more in-depth reasoning, especially for tougher tasks. This is why they then do that online RL phase to refine the learning process even further.
Okay, so that leads us to the second phase, the rule-based online reinforcement learning. How does this phase actually reinforce that reward generation process?
So for this part, they use the GRPO framework, but with a key difference. Instead of format-based rewards, they use rule-based outcome rewards. The GRM is still generating principles and critiques based on the input query and responses, and the predicted reward is pulled out and checked against the ground truth using accuracy rules. These rules are defined in equation 5. Basically, if the predicted best response matches the actual best response, or if the predicted reward for a single response matches the ground truth, then the model gets a positive reward. If it's wrong, it gets a negative reward. It's important to note that the model isn't directly rewarded for formatting its principles or critiques in a specific way. Instead, they use a bigger coefficient for the KL penalty during training. This ensures that the output is coherent and helps to avoid biases. The main goal here is to directly encourage the GRM to get better at identifying the best responses based on the principles and critiques it's coming up with on the fly.
The paper talks about unpinning principles from understanding to generation. Can you explain what that means and why it's important for getting the scalable reward generation?
This is where they really shift how we think about generating principles. Before, we might have thought of it as a separate step, maybe even something that was set in stone beforehand. You'd have a fixed list of principles, and the reward model would then apply those to evaluate the responses. But the authors are saying, no, let's make generating those principles part of the reward generation process itself. They formalize this in equation 3. The big innovation here is that the function that's generating the principles, which they call pay, actually uses the same underlying model parameters as the reward generation function. Because the parameters are shared, the principles can be generated dynamically, based on the specific input query and the responses that are being evaluated. This allows the principles to be more relevant to the context and tailored to the specific situation, which can lead to more accurate and nuanced reward signals. And as the model goes through training during SPCT, its ability to both generate good principles and produce accurate critiques gets better together. It's like instead of having a static checklist, the model learns to come up with the right criteria on the spot for each new input it sees.
Okay, so they've got this framework set up, and now the paper looks at how to use more computing power to boost the performance of these DeepSeek-GRM models even more. They focus on methods that involve sampling. The first technique they talk about is voting with generated rewards. How does that one work?
So as shown in equation 6, the basic idea is to run multiple inference passes. Each time, the GRM comes up with a set of principles and the critiques that go along with them, which leads to individual reward scores for each response. Then, to get the final reward for a response, they add up all those individual scores from every sampling iteration. Because those individual scores usually fall within a limited range, like 1 to 10, this voting system effectively expands the possible range of rewards. The thinking is that by generating a bigger and more diverse set of principles through repeated sampling, the model gets a better, more refined judgment that's closer to how a variety of different evaluators might score the responses. And to avoid any bias from the order of the responses, the paper mentions shuffling them before each round of sampling.
Then they present this second, more advanced scaling technique. Meta-reward modeling guided voting. What's the core concept there?
This one builds on that basic voting idea. They train a separate meta-reward model, which is basically a pointwise scalar RM, to specifically judge how correct or how good the principles and critiques are that the main DeepSeek GRM is producing. They train this meta-RM using binary cross-entropy loss and data from two sources: the non-hinted samples from the rejective fine-tuning stage and the DeepSeek GRM itself as it's being trained. Here's how the guided voting works. Just like in the regular voting, the DeepSeek GRM generates multiple sets of principles, critiques, and therefore rewards for a given query and set of responses. But then the meta-RM steps in and evaluates each of these generated rewards, giving it a meta-reward score. This score basically reflects how reliable or how high quality that particular reward signal is. And in the end, the final decision is made by voting only among the top koi meta samples, the ones that got the highest meta-reward scores from that meta-RM. This filtering step helps to get rid of any samples that might be biased or just low quality, so the final decision is based on the most trustworthy evaluations.
All right, let's move on to how well this all actually worked. The paper presents a whole bunch of results from various benchmark tests for reward modeling. What were the main takeaways regarding how the DeepSeek GRM model stacked up against the existing methods?
They've got it all laid out in Table 2. The results show that even without using any inference-time scaling, the DeepSeek-GRM27B model generally performs better than the baseline methods the authors re-implemented, and it's on par with some really strong publicly available reward models, like Nemrtron 4340B Reward and GPT-4o. Interestingly, the scalar and semi-scalar RMs that were used for comparison showed some biases. They were really good at tasks with easily verifiable answers, but struggled with those more open-ended tasks. DeepSeek-GRM, being a generative model, seems to be more consistent across all the different benchmarks. And crucially, once they applied those inference-time scaling techniques, either the straightforward voting or the meta-RM guided voting, DeepSeek-GRM27B achieved the absolute best overall results across all the benchmarks they tested.
Right, and then Figure 1 and Table 3 zoom in specifically on those inference-time scalability results. What were some of the most important things you noticed there?
The most striking thing was just how much DeepSeek GRM27B improved as they increased the number of inference samples up to 8. And it was clear that there was potential for it to keep getting better even with 32 samples. That meta-RM guided voting consistently helped to boost the scaling performance. They also looked at other models. For instance, LM as a judge did show some improvement when voting based on token probabilities. But CloudGemma 227B didn't scale well, even though its critiques were varied. The authors think this is because the scalar rewards it generated didn't have much variance.
They also did an ablation study, which they show in Table 4, to see how the different parts of SPCT contribute to its overall performance. What were the key takeaways from that analysis?
Well, they learned a few important things. Firstly, even without doing the rejective fine-tuning cold start, the GRM still got significantly better after that rule-based online RL phase. Its overall performance jumped from 66.1 to 68.7, which shows how crucial that online RL stage is. They also found that the non-hinted sampling during RFT seemed to be more important than the hinted sampling. This might be because, like we talked about earlier, hinted sampling can sometimes lead to the model not engaging in more robust reasoning. The study also showed how important using general instruction data is for the GRM's overall performance. And going back to scalability, they found that the principal generation component was essential for DeepSeek GRM27B's performance, both when it was using standard greedy decoding and when they applied those inference-time scaling methods. Lastly, that meta-RM guided voting turned out to be really robust, performing well even when they changed the value of that Cometa hyperparameter.
And finally, Figure 4 compares what happens when you scale up the inference compute versus scaling up the model size. What did they find there?
The results on the reward benchmark were pretty interesting. They found that just by giving the DeepSeek GRM27B model more processing power during inference, either by using 32 samples with direct voting or just 8 samples with a meta-RM guided voting, it could perform just as well as or even better than models that were much bigger, like models with up to 671 billion parameters. This really highlights how powerful effective inference timescaling can be as a strategy. They also tested DeepSeek-R1, which is a really big model focused on reasoning, and found that it wasn't as good as they expected at these generalist RM tasks. This suggests that simply scaling up chain-of-thought reasoning might not be the best way to go for generalist reward modeling.
So to sum up all this research we've covered, what's the main takeaway for our listeners?
The most important thing is this new method they've introduced, self-principled critique tuning.
or SPCT. It's a really promising way to make generalist reward models much better at scaling during inference. By letting the model adaptively generate principles and critiques, SBCT leads to big improvements in both the quality and the scalability of the rewards. And they showed this really convincingly with their DeepSeek-GRM models across a range of tough benchmark tests. And adding that meta reward model to guide the voting process gives it another performance boost.
Right. And while the paper does point out some limitations, like the fact that generative models aren't as efficient as scalar models, and that there's still some performance gaps on very specific tasks where the answer can be easily verified, they also highlight some exciting areas for future research. Absolutely. They suggest looking into things like incorporating external tools into the reward models, which could help with tasks that need access to outside information or have to follow strict procedures. They also think it's worth exploring ways to generate principles and critiques separately, which might improve efficiency. Plus, they see a lot of potential in using these advanced GRMs for offline evaluation of LLMs and even for tackling those more complex long-horizon reasoning problems.
So, as we wrap up this deep dive, here's something to think about. Given all this progress in inference-time scalable reward modeling, how might this completely change not only the way we approach aligning RL-based LLMs, but also other crucial areas in your own work where having really robust and adaptable evaluation methods is super important? Think about what it could mean for what you're doing now and the new paths for investigation that this research might open up.